We are at the chapter 3. We are talking about the analysis of frames. And the frame we are considering one has no side sway and another one has the side sway. How come? The frame usually, if the frame is symmetry, the shape of the frame is symmetry, and it is subjected to the symmetric load like this. This kind of frame is the frame with no side sway. Typically, the frame has no side sway if this frame subjected to non-symmetric load, but is less than or supported by the pin and the fixed support like this. Okay, the frame 3 of this frame has no side sway. Typically, the frame has side sway. What is the side sway? Side sway usually is the linear displacement of the frame when the frame subjected to the such as wind load. If we consider this frame, okay, this frame is the frame as the harbor in Rayong, for example, and then this kind of frame will subjected to lateral load from the wind. Okay, we may call it the wind load. That's from the lateral. This kind of frame has the side sway because the wind will blow the frame, and the frame will has this kind of linear displacement, and then the frame will deform in the shape according to the support and joints it uses. Okay, even though the frame is in the shape like this, okay, and then when the load is symmetry, even though the load is passing through the half of the structure, this frame also has the side sway. Since the column on this left hand side is taller, if the beam has the constant EI, the frame may have this kind of elastic curve. Okay, I can now redraw this because we want to check whether the frame going to be the frame with the side sway or the frame with no side sway. We have mentioned about the frame with no side sway. We can analyze it as similar to the beam. But the frame with side sway, the method of moment distribution must be modified to taking care of moment distribution. Sorry, moment distribution. Sorry, must be modified to taking care of the lateral or linear displacement. How should we modify it? The method of moment distribution when it's developed is start by considering the member stiffness factor. You know this one is the member stiffness factor. There is two member stiffness factor in our consideration. Is come from the equation of slope deflection. One is based on 4EI over L, and another one based on 3EI over L. For the member that has the external pin like this, you will use 3EI over L, and this one 3EI over L. But typically, when you consider the beam such as this one inside the structure, is going to be 4EI over L, or if your column has the fixed end, it's going to be 4EI over L, okay, in the consideration. And by doing this, we never consider the linear displacement in the consideration of the member stiffness factor. That's why when we analyze the frame in in this manner, we are supposed to modify it. How do we modify it? I will talking about later, but we will discuss about the problem that we may have in this study. Okay, I should classify the frame into one have equal column, equal length column. Okay, and another one is going to have unequal length column, and you may see the one that has the unequal length column going to be here, and the equal length column going to be here. And then when we consider the frame based on the support, we may have the frame with supports by the pin. Okay, it can be pin, or it can be fixed, such as we have in these two problems. And then you still have some other, such as the frame that has fixed and pin, or the frame that has fixed and pin like this. Okay, when we consider this kind of structure again, you're going to use your knowledge to consider the frame or analyze the frame based on we learn based on this. This is going to be 4EI over L. This is going to be 3EI over L. This is going to be 4EI over L. Okay, but this one 3EI over L, and the rest of these two is going to be 4EI over L. And the frame also, not only the support, it has the joint. Sometimes the frame has the internal hinge inside it. For example, if we have the frame and then we have the hinge like this, we put the hinge over here. By putting the hinge over here under the application of the force, then you're going to consider the frame. This frame going to have to use 4EI over L for this column, but due to the hinge, these two members, the beam and the column, you're supposed to use 2EI over L. I mentioned about this because if you select the wrong case, you're going to in a bad shape. Okay, and then when you select the 4EI over L, your fixed end moment will basis on this kind of fixed end moment. Okay, it's going to be fixed. However, when you use the 3EI over L, your fixed end moment will come from the member that has external roller or external pin to determine your fixed end moment. Okay, we finished talking about the type of problem that we have. Let me illustrate some of this. And then, since we didn't consider the linear displacement in this kind of frame with sidesway, what we supposed to do? Professor Harry Cross said we're going to use the principle of superposition. We're gonna separate the frame. For example, let us consider the frame that is the most basic one. Let's say it's going to be fixed, and then is subjected to the wind load like this. I will have this example later. Since the frame under the force is going to deform like this, and then the frame has the sidesway delta, and then by the principle of superposition, Professor Harry says we are going to separate the frame into two frames. One, we will let stand it from the sidesway. Another one, we will let it have the sidesway. Okay, by doing this, we just separate this one into two frames. The first frame will subject it to the given load. Okay, and then we are going to let stand it from sidesway. Okay, by analysis of this, the external load will produce the fixed end moment to the member of the frame, and this fixed end moment will produce the end moment M super naught like this, and the M super naught will bring us to determine the resistance force, the resistance force for the linear displacement. Okay, so we will get the value of this, and in reality we must put the resistance force into the next frame, and to let this frame has the sidesway of delta in which all the beam must be in the horizontal like this, and then we have the lateral, okay, delta displacement. By doing this, we don't know again the value of this. Even though you put the R here, you cannot solve this problem. So another way, Professor said, you gonna assume what? Assume the delta. If you assume the delta, you will get the fixed end moment for this one is going to be fixed rate. It's going to be EI, let's say delta palm, divided by L squared. That is two way. You may assume the delta palm, or it's better for you to assume the fixed end moment because it's directly hit the problem. So when you assume the fixed end moment, you also assume the delta palm. But when you assume the delta palm, you must plug into this equation to find the fixed end moment to compute for the M palm. And then for the M palm, you will compute for the R palm. So this one is going to be the R palm. R palm is not real. R palm is come from the assumed fixed end moment. So by the principle of superposition, you have what? You have this point. Let's say this is C. You do the summation of force in the X direction equal to 0 at C. Okay, this is what is 0. You have 0, and this is equal, and this is the R. Okay, and this is in the opposite direction. You got this one for minus R palm. Since this is not real, you got to have the correction factor. So Professor Harry Cross proposed the C, and then you can compute the C as the R divided by R palm, and you use this C to adjust your M palm. Okay, so now the moment here is going to be equal to the moment here, M super naught, and then plus C, and then times the M palm. You will have the moment occur in your problem. Okay, the computation going to involve two moment distribution. One is required for you guys to determine M super naught. Another one require you guys to determine M palm. Okay, so the problem of the frame with sidesway will require more effort to solve compared to the frame with no sidesway, which is similar to the beam. So in examination, try to work on the beam first, and second, work on the frame. Okay, in the PowerPoint, okay, we have this frame. This frame is unequal column frame, and we are going to use the moment distribution to analyze the frame. Okay, this frame special, not only unequal column, it also have different moment of inertia. Okay, this frame made by the steel because the modulus of elasticity is 200 gigapascal. So what is the degree of indeterminacy of this frame? Okay, it's going to have fixed at A and fixed at D total 6 unknown reaction, and you have 3 equations of equilibrium for one free body diagram of this frame. So the degree of indeterminacy going to be 3. How about the degree of freedom? If you consider the degree of freedom, you can do the consider how the structure different under the rule. Since this column is long, okay, and the stiffness and the stiffness of the column based on EI over L. Okay, maybe 4 here. Anyway, since the L of this AB column is large, so this column should have smaller or less stiffness than the column CD. So I believe this same view will have the sidesway like this. Okay, and basis on the rigid joint, this one must keep itself in the normal angle. And also, if you consider the shorter column, I believe it's maybe deformed something like this. And again, it must be kept in this normal angle because the joint is both B and C, the rigid joint. Okay, and then since the load applied like this, due to the flexibility of this one is supposed to be concave downward, and another portion should concave upward, and this one will concave downward, and you can draft the elastic curve of this frame like this. It may not be correct because you don't have the moment diagram yet. That is give you the idea. Idea of what? Idea the frame is going to have some sidesway to the left. Okay, and based on this analysis, this is going to have theta sub B here, has the delta and delta over here, and theta sub C. So the degree of freedom going to be theta B, theta C, and delta B equal to delta C equal to delta. Why they are equal? Because the axial deformation of the beam and the column on this analysis is very small. When it's very small, they are equal. So we have the degree of indefinitency like this. We have the frame with sidesway, and we have the degree of freedom like this. When we consider this, that means you are going to use 4EI over L, 4EI over L, and 4EI over L for the member of this frame. Okay. If, for example, if Ajahn just check this fixed end into the pin, you may have another problem. You may just try to solve it. Okay. Or if I just change the A and D, both of them are pins, you can solve another problem. Okay. Okay, by doing this, I got the K, and then I will start to determine the K. However, since the IAB not equal to IBC and different from the ICD, we're supposed to set one cockpit, okay, to be the left lane. Let's the bigger one, the I sub BC is going to be the full I. So this one will be equal 0.5 I sub BC because it's only half. And this one is going to be 320 divided by 480 I sub BC. You can determine the relative between them easily. And then you may have I sub AB equal to 2/3. Okay, this one is going to be 2, and this one is going to be 1/3. Okay, 2/3 of the I sub BC. And then for the I sub CD, you have 0.5, and you start with the principle of superposition. Separate the frame into 2 frames. One unit stand kit from the fourth shift. The frame has the sidesway in this direction. So your resistance force will require in the opposite direction. And you said this is going to be the resistance force. Now, the frame will subjected to the external load of what? Of 37.5 kilonewton meter. This external load will produce the fixed end moment to the member BC. So it's going to have fixed end moment BC and also fixed end moment CB, and you can do the what moment distribution do the moment distribution, and then you get M super or not over here. And from the M super not, you can use the free body diagram, okay, and the equation of equilibrium to determine the resistance force. And the other frame, we will let the frame to have the sidesway. Okay, we have the sidesway. This sidesway delta will be provided by the force of R. Okay, but even though you know the force of R, but you don't know the delta, you cannot determine the fixed end moment that occur in the structure. So for this one again, you just let your frame deform. Okay, when the frame has this kind of delta, the beam has no change in shape. Okay, because the shape of beam has changes already from the first case. By doing this, you have the fixed, and you're going to assume the fixed end moment. Okay, by unequal length column, the assumed fixed end moment going to be a little bit complicated when compared to the equal length column. For example, if you set the fixed end moment for this one, let's say if you set this one to be 100, the fixed end moment that occur here will be less than 100 because what? Because the stiffness that I just mentioned before of this column AB is smaller than the stiffness of the column CD. So you got to do some calculation. You may assume one of the fixed end moment on one column and determine the fixed end moment on the other column. And then when you finish determining, you're going to do the moment distribution for the second time. The first time is here. This is going to be the second time to find M palm. And then you use the free body diagram and you use the equation of equilibrium to determine R palm. This R palm is come from the assumed fixed end moment. It's not real. You're going to go back to the principle of superposition. Do the summation of x sub x at equal to 0 at b, okay, or at b equal to 0. And then you may have what? This one has no force, 0 equal to R, okay, and then this one going to be minus R palm. And then you got to put the correction factor to take care of this. So you have this one as the correction factor. So you can determine the correction factor to be R divided by R palm. And then you come over here, you adjust M palm by the C M palm. Now, the actual moment that you are looking for over here will be equal M super naught, okay, M super naught, and then plus C M palm. That is going to be the end moment of this frame. Okay, over here we going to determine the stiffness member's factor in order us to do the moment distribution two times. The first one, 4EI over L for the column AB, and then you have 2 over 3 I sub BC, just put it, that is 409 EI sub BC. For the beam BC, E4 EI sub BC over 9.6, so it's going to be 4 EI sub BC divided 9.6. For the column CD, it's 0.4. And then this is 0.5 I sub BC divided by 4. So you have the member stiffness factor. And I'd like to mention a little bit about the stiffness going to be this member. And then this is going to be the second. And this is going to be the smallest stiffness. And then you go further to determine the distribution factor. Now we have what? We have the fixed end of this, and we have the fixed end of this. The distribution factor AB will equal to the distribution factor DC. It's going to be 0 because it's fixed. If I change it to pin, the distribution factor will be 1.0. Okay, and just change the support, even though you has the same load. The analysis of the problem going to change. Okay, so you guys are supposed to be open-minded and then concentrated on the concept of the problem. And now we go a little bit further to distribution factor here. That is going to be the distribution factor BA. The distribution factor BA gonna come from K sub AB over here, divided by K sub AB and plus the stiffness of this member K sub BC. So you just plug everything into this equation, you get 0.5161, and then all of the distribution factor BC plus distribution factor BA, all of them must be 1, and then the light blue distribution factor, just put this one 1 minus 0.15, and then you will get, okay, the distribution factor for the member BC. Okay, and now for the C over here, CB, okay, just move it a little bit. This one is going to be the distribution factor CB, and you will determine from the stiffness of this member is going to be K sub BC divided by K sub BC plus the stiffness of this one K sub CD. Okay, you got this one, and you plug everything into this equation, you get it 0.4545. And the last one for this portion, you will get the distribution factor, just 1 minus 0.4545, you get 0.5455. Now you're going to find a fixed end moment. And this is very easy. Just take the fixed end moment. That's fixed end moment sub BC going to be the UL square over 12. Just plug it, and BC going to be negative. CB is going to be positive. Okay, this is going to be negative 288. This is going to be positive 288. And then we are ready for the moment distribution. We plug the distribution factor and the fixed end moment to our table. And the first one is going to be distributed moment. Oh, this is wrong. This is going to be 0. You plug this one and consider the equilibrium of each joint. Okay, this one is fine. There is nothing. How about this one? This one you gonna require positive 288. Okay, and the positive 288 come from the stiffness of each member. Take 288 times the distribution factor, you get this one. You take another time, you get this one, and then when you get these two, this guy just gone. Okay, I will show this later. And then you come over here, you will require minus 288. Since it's going to require minus 288, you know immediately the sign over here gonna be minus, and you time this one and take it down. You time this one and take it down, and then you get the distributed moment. Okay, and let me illustrate of this distribution, and you get everything. This is positive, and this is negative, and the author here gonna be negative. Now when you have the moment, you got to do further. You got to do what? You got to do the carry over moment For example, the moment occur at this point, which is going to be 148.64, it must be carried over to this one. And for this moment at the CD is occur here, okay, it must be carried over to this side. And although we has the moment 139.36 over here is gonna carry over here, and you got minus 130.90 is over here, is must carry over here. Okay, that is for the light blue, and that is for the green. When you do the carry over, okay, you got to time the moment by 0.5. It's going to be reduced by a half, but the sign is going to be the same. This is positive, this is going to be negative, this is going to be positive, this is going to be negative, and then you get the result like this. Okay, let me illustrate this a little bit so make it clearer, pointing out the sign you're supposed to taking care of. And then we do what? We do another distributed moment. We distribute the moment again. And we know this one can require minus 74.32, but this one has fixed end. So you times 0. This is 0. Okay? Is take off the moment. No distribution is also occur over here. Okay, the occur over here, you require plus 78.55 times 0 is gonna be 0 here. So that's point A in equilibrium, and also point B in equilibrium. Next, we come to this one. Okay, the choice B, subjected to unbalanced moment, and since the unbalanced moment is negative, so it's required positive 65.45, positive 65.45 times this one, you get this value, times this one, you get this value, and then you just move a little bit more to this portion, and then if you notice, this one has the positive, so to balance it, you got to get negative here and negative here, and you time this one by this one, you get this one, time this one by this one, you get this value, and then you get all of what you should have. Just put things in the calculator and do the careful calculation to get the answer. This two positive, this two negative, to balance everything. Okay, so this is wrong. This, the sheet here is not correct. Okay, just put negative here. The result will be correct. And you just do this. Do what? Do again for the carry over moment. Now you do the carry over moment, and you repeat what you have considered. The moment 33.78 will carry over here, and this one will minus 38.01 divided by 2. This one going to be positive 33/78 by half. Okay, and then you do again for this one, for this light blue. This one move over here, and the green just move half into this portion, and then you do the same thing. Just consider the equilibrium of each joint and do the same repeated calculation. Do it carefully. Okay, it's going to produce the skill to you on this kind of calculation. You do it like this, and finally you get the answer of the end moment when you extend the frame from sidesway. Now you're going to use this one. Okay, again, let me tell you again. We have what? We have the frame like this. Okay, our frame subjected to 37.5 kilonewton meter, and now our frame is going to sidesway in this direction, and then you said you are going to determine the resistance force R. When this resistance R from what? That is going to be resisted by the force A sub x here and the force D sub x here. Where the force come from? The A sub x will come from the moment over here, okay, and those two moments going to rotate clockwise because they are positive. And now if it's rotate clockwise, the A sub x supposed to be in this direction. And again, let me illustrate a little bit and put the correct direction here. And later for the column CD, you just draw the free body diagram DC, and all of them produce the negative moment, so it's going to be counterclockwise. Okay, this is going to be M sub DC, and this is going to be M sub CD, and then your force over here gonna be D sub X. So this D sub X is correct. Now you can just use the summation of X sub X equal to 0. You are plus A sub X minus D sub X equal to 0. So you can determine R, okay, easily. So you plus A sub X and minus D sub X. Now repeat the process. Just go to the free body diagram of the column AB and column not AB and the column CD. For the column AB, okay, let's see the same as we have. This force V A sub X will times 6, okay, and then it's going to equal to the two moment plus, and then you get A sub X of this, and D sub X do the same thing. You get like this, and then you sum them. No, you do the summation of them by the summation of X sub X equal to 0. You can determine the R, okay, plus A sub X minus D sub X equal to 0. So your resistance force for the sidesway going to be 29.167. And then I need to go further. We must assume the fixed end moment for this case. Again, this is the shape of the deflected shape when the frame has the sidesway. And again, I should call the sidesway to be the horizontal linear displacement. Okay, you can see, and then the direction of this one will follow the force R palm, even though we don't know, even though you put the R over here, you cannot solve it. So you got to assume the fixed end moment. No. Oh, okay, yeah. When you assume, which one you can assume? The problem will give you in the examination. Ajahn will provide you the fixed end moment, and you just follow what Ajahn assume. Let me assume this one to be 100. Okay, for the short column, which is stiffer than the long column. So the fixed end moment that's gonna occur in this one, the yellow, is going to be smaller than the green. Okay, and another thing about the direction of the fixed end moment. Why Ajahn know the direction of this? You just bring your projector And if you move like this, you can see the deflected curve of the column is like this. So the deflection will be as I draw over there for the green and for the yellow. So we assume the first one to be fixed end moment DC equal to fixed end moment CD equal to, this is positive 100 because it's rotate clockwise direction. Okay, and this is going to be equal what? This is going to be equal to 6 EI delta palm over here divided by its length. Okay, if I correct, that's supposed to be 5 and then square. Okay, and then you just plug it equal 100 and you are looking for the EI sub DC delta palm. Okay, and by doing this, I sub DC is 0.75 I sub AB. This is important. Okay, important to understand. Let's you take this I sub DC. Okay, I sub DC is 0.75 I sub AB. Beware about this. A lot of students make a mistake of this. Okay, and then you can find what? You can find it I sub AB delta palm. Okay, just plug it. So you can find EI sub AB delta palm. That means you looking for this delta palm. And then since this one also delta palm, the fixed end moment occur here going to be 6 EI sub AB delta palm divided by length square. Now, like I said, the EI sub AB delta palm, they must be plugged into this equation. And then you do the computation. You get what? You get the fixed end moment over here of 59.26. As I said, this is smaller because the stiffness of this column is less than the stiffness of the column CD. You should have set on this. And then all the moment that occur on these two columns is 100. And the moment that occur on these two columns is going to be 59.26. This fixed end moment must have distributed. Okay, so we start by consider this one, and this one times 0 is going to be 0. Then we go to the choice B, and you can see that the unbalanced moment is positive, so it's require negative moment. Just time this, plug into here, and then just time this and plug into here, and then go further to this 100 kilonewton unbalanced moment. So make it to be negative. This is going to be negative 45.45. This is going to be negative 54.55. Okay, and the last one, this will produce 0 because this one times 0 make this one to be 0. So you get this. Okay, you guess what we always do, but you got to do it carefully. Okay, to get everything correct. Now, the obtain distributed moment, they must be carry over, and then it's going to be carry over moment, and it's going to be the same as we did from the previous moment distribution. If you may recall, you just go back and redo it again. Okay, from the first table, just copy all the color and plug it like this, and this one will reduce by half, this one will reduce by half, everything going to be reduced by half, and keep the sign, okay, as before. And now it starts to be the unbalanced moment. Okay, this is going to be the second. You do the distributed movement. This is called the first round. This called the second round. Okay, this is going to be the first round, and this is going to be the second round. And the balance of the moment here gonna be 0. This is gonna be 0. The author, you're going to have following this negative moment, you're going to require the positive here, also positive here, and positive here. You do the computation, you get all positive, and then the moment occur on the joint going to be in equilibrium. And again, the process go to the carry over moment again. Carry over moment, and then this is going to be the third round. Okay, you do the same process of what carry like this, and the author gonna be like this. When you do it untilอาจารย์give it round. Okay, this one going to be 1 round, 2 round, 3 round, and then this is going to be 4 round and 4 and 5. This is going to be 5. This is going to be 6. That is many round of kit, and then you get this one to be the again the end moment, and then it's require you to determine the force that occur at A and D basis upon this for the column AB and BA. Okay, AB is going to be this way. This is going to be 49.28. This is going to be 39.31, and you can see clearly by this rotation the horizontal force A sub X must be in this direction, and it's going to be the summation 39.31 plus 49.28 and divide by the length of this column. Okay, divide by the length of this column, and then divide by this, and then you come to the other part of this. This is going to be the positive moment also. This is positive, and this is also positive. So by doing this, the D sub X must be in this direction. So you get the D sub X and A sub X by computation like this. Oh, sorry, it's not 6, it's not 7, it's 6. This is going to be 6. Okay, and then you do the same computation, and then for the summation of the force, the R palm is going to be 46.223. Now you can compute the correction factor based on the principle of superposition. Again, the force that occur on this point is 0. Is going to be equal to this force plus this one, which is in opposite direction, and then you got to put the correction factor C palm to adjust this force that come from the assumed fixed moment, and then you get C palm equal to 0.6T101. Notice what? Notice the significant number that I use. If you won't use the ratio, you're going to use 4 or 5 significant figure for the C palm, and then you do the computation. This is actual, is come from the applied loading, and this is not actual, is assumed from the assumed fixed end moment. So it must be correct into this one. Okay, and then you use the yellow and the light blue to sum up to be the final end moment. And I like to mention again, you're gonna be very careful when you taking care of this free body diagram of the column. Okay, this is going to be A, B, B, C, C, D, and now let's say this one will put into this direction with the this direction, that is 127.60, and then this one must be in this way, is going to be to 17.82, and then go to this one going to be in the negative. That means it's going to be counterclockwise, and then you can check these two moments must be equal. Okay, that is going to be 217.82, and then you may elapse some object to make it a little bit clearer. And what we have, the moment here is what is positive clockwise 174.56. Again, this is going to be balance moment, okay, in the counterclockwise direction. And the last one that you see is this one is going to be what is going to be counterclockwise 55.72. And then don't forget about the applied loading that you must put into the free body diagram, and then you determine the end shear of this one. This one rotate like this, you for sure this is going to be A sub X, and this one going to rotate like this one going to be D sub X. And don't forget this load will transfer across the joint. Okay, it's going to be downward here and upward here, and it's going to be downward here, and it's going to be produce the A sub Y here. So you get these three as the reaction of the frame. Again, this one also you get the joint. This one upward, downward, upward, and then downward and downward. You get this one for the D sub Y. And sometimes I also ask you for the reaction. Why Ajahn asks you for the reaction? Because the reaction will use to design the what? To design the foundation, and the pie, okay, for the support A and for the support D. And then since you need to connect, okay, the column to the foundation, you also require to design the support, okay, design the bold, design the detail of the connection. Okay, so next you just go a little bit further to draw the shear diagram and moment diagram. And I like to mention again, to draw the shear diagram or the moment diagram, you require to put the value and you require to put the slope into the graph. Why? Because the slope such as dv by dx equal to minus w will give you the shape of this one. Okay, and then you have the equation v sub b minus v sub a equal to minus of the area of what? Area of w between a to b. That's for finding the value of the shear. And then for the force that's upward, the delta v is positive. For the force downward, delta v is negative. Okay, and then come into this again. You have dm by dx equal to v, and m sub b minus m sub a is the area. This is have negative, this have no negative, okay, because this is plus area of v diagram between a to b. And last one, if you have this moment, okay, this moment, you are going to have delta m positive. And if you have this kind of moment, you have delta m negative. Okay, and now you come to what we have here. This 126.6 is going to be clockwise, it's going to be positive. Okay, this is positive. See, and this 55.72 is counterclockwise, is going to be in the negative. See, okay, that's telling us a lot about the moment. And then a little bit further, you can see 217.82 over here. So this is going to show us this one 217.73 and 174.536. You can determine from here. So you get a lot of things. The end moment already appear in the moment diagram. But you got to give me the slope in order to explain the shape of this shear diagram and moment diagram. Okay, so what we have is what this one, the a sub x will be negative, like this one 57.53. we know the value of this one, and then you got to say this is going to be dv by dx equal to 0, and provide me the sign of it. Okay, and then when you come over here, you have this one going to be dv by dx equal to the negative of 37.5, and you must say this is 0. This is 0, must be 0, because you got to tell me clearly where is the point of this 0 shear. Because of what? Because it's going to produce the maximum moment here. And then the slope, you just tell me by marking something like this to make it to be the linear equation. And then based on this, you have this one for 184.5, and this one for x, you have 184.5 divided by x is going to be slope. Okay, so this x is going to be 184.5 divided by 37.5. Okay, and the last one, if you go a little further, the direction of d sub x, see, is put on the left hand side. So it's going to be like this with 57.533, and then you got to tell me for dv by dx equal to 0. Again, everybody know about it? No, you got to show your understanding, not everybody. Okay, and now since you know the moment here, okay, to be positive, like I put 127.6, like this is clockwise. So when it clockwise, it's going to be positive. And you got to show again, this is going to be dm by dx equal to what? Equal to minus 57.33. And it's going to be minus, and then minus, and this value, don't do the computation, you know it already. Let I show you here. Okay, that is by this direction. When you put the sign convention for the static, you can see this one follow the same direction. So you move to the equal sign to the right, you get the negative 217.82 as shown over here, and two of this going to be equal. And then you go to this one, and you know the value of what? You know the value of the moment here, but you got to say this one dm by dx equal to what? Equal to this value of positive 184.5. See, it's positive, okay, and it's going to be smaller and smaller, and hit over here to be the dm by dx equal to 0. There is no slope here. That's provide the maximum. So the m over here minus 217.731, and then this is going to be the area here, 1/2 of this one, okay, and then it's going to times 184.7, and then you will get M equal to kilonewton meter. That's why we going to specify this kind of thing. And then the moment here, you know, from the graph, from the free body diagram here, okay, is going to be this direction. You follow what you have. You can draw this one, okay. You can draw this one. You can draw this one of what? That's the one of the beam, okay. It's going to be this one, not this one, not this one, this one, and the moment here and here follow the same direction, so it's going to get negative here, okay. And following this, you have the dm by dx equal to the value here of minus 175.5. Again, the last one, this is a positive, this is a positive. So let me put the slope here, and slope here, and then you have the dm by dx equal to v 57 plus, this is positive, plus 57.33. That's going to mark you the whole full score. And then you know a little bit more about this point of zero moment. Put the zero moment here, it's going to be the inflection point, okay, point, and is used to change the moment, okay, from this positive to this negative, is change the curve like this, okay, and then it's going to curve back like this. And then when we talking about the reinforcement, we're going to put the different reinforcement. This one you will put on this side and cut at this point, and this one you put in this side, more steel than the typical one. And then we can do a little bit further. Let I talking a little bit more about the reaction, okay. We're going to use this to design the foundation, design the connection over here. And one more thing, let you guys also know the axial force diagram, even though Ajahn didn't ask is much, but I like to mention, if the column is subjected to the axial load, okay, we call this for sure is the column. However, if the column not only in the compression but is also subjected to the bending like this called the beam column, okay, this called the beam column. The beam column has special treatment because this beam can buckling easily. So when you study the steel design, they're going to separate the design of the steel, then side of the reinforced concrete into the column, into the beam column, and the beam column also equivalent to what's so-called the slender column, okay. And for the typical column, actually they just leave it. It's called short column. They are different. So I should finish the PowerPoint over here, okay, and I'm going to show you guys another example, but I'm going to use the virtual presenter to show you this, okay. But for the other thing, you just go back to read yourself about this more example. For now, we concentrated on what we have in our scope of study, and for the frame with the inclined column, okay, we will talking about for the more advanced course. Okay, now let me move a little bit to this problem. You guys may have this one before. I modify this one by taking the point load out in order to have your guy a chance to solve this problem with the 10 kilonewton force over here. Okay, just for you to have more exercise on this. The frame has what? Has the fixed support at A, okay, and also has the fixed support at B. So this steel frame will have the degree of indeterminacy of 3. And again, it's very similar to what we have in the previous one. The degree of freedom of this one is going to be a little bit easier to predict the sidesway of this. Okay, we can see this one is fixed, this one is fixed. The wind, the lateral like this, maybe the wind is going to blow the frame like this. I believe it's maybe like this. And then we have the sidesway delta. We have the sidesway delta over here. And this one will keep its angle to be normal. And I guess this one may have the deflection, something like this. Okay, and this one going to be the inflection point, the inflection point. The depth of this may be wrong, but don't worry. We will have the moment diagram, and we can use the moment diagram to clarify what's supposed to be the inflection point on this frame. So this one gonna be theta sub C, slope over here, theta sub D over here, and the sidesway delta. So the frame has the sidesway. We're going to use the specific method to solve this. Okay. What should we start? Since the frame has the sidesway, you should mention about the principle of superposition, because you got to separate the frame into two frames, one with less than from the sidesway, another one going to be sidesway only. So this one will equal, just let me put all of them 5 meters. Just say this is 5 meters, 5 meters for 20 millimeters. I will put all of this have equal length column. Okay. So you can solve this one by separate this one. Okay. Principle of superposition, you separate the frame into two cases as shown. Okay, and WN. And then what we have is, again, we got to less than the first one. Under the application of 3 kilonewton per meter, the wind will blow to the structure like this. That means you got to put this roller to resist the sidesway in order you to use the method of moment distribution to solve this problem. Okay, and then let's say this one the R, and the other one the structure will require to have the sidesway. Let it sidesway for 5 millimeters. This is going to be the delta, and this is fixed. And since this portion of the beam has been deflected already, so this one must be only the delta. So this is going to be just laterally move, and then the deformation of this one supposed to be in the shape like this. Okay, and then what we have is to make it to be moved by the delta must be the force over here. Actually it's supposed to be R, but if you put this one R, you have the problem. You cannot determine the fixed end moment of this. So you will assume the delta, or we will assume the fixed end moment. It's better for us to assume the fixed end moment. Let's say FEN palm, and then we can determine this one R palm. Okay, for this one you have the fixed end moment due to the loading, and then you can determine the M super knot, and from the M super knot you can determine the force R. This consider the case one. For this one you assume this one, and then you use the moment distribution. You find M palm, and then from the M palm you use the free body diagram and the equation of equilibrium to determine R palm. Okay, both of this can use to determine this, and then you use the summation of x sub x at what? At this point of d dot, this point of d dot, this point of d dot, at d equal to 0. You can see this has no force, 0, and then it's going to be equal to what? Equal to R over here, and then this one has the opposite direction, minus R palm, and then you got to put the correction factor due to the assumed fixed end moment. So the C is going to be R divided by R palm, and we will determine this for what? For computation. For first, you got to use to adjust this, and then the moment here gonna be equal to moment M super knot, and then it's going to plus this one gonna be C, and then it's going to time M palm over here, and then you get this end moment for the frame that we are considering. Okay, if everybody understand the basic of this problem, let us start by compute of the K. Okay, by consider this problem, this is fixed, this is fixed. You're going to use 4EI over L, 4EI over L, and 4EI over L. Again, I like you guys to go back this same problem. Just change this one to pin. Thinking about it. Think this one to fix, pin. Change this one to pin, fix, or more. If you have time, change this one fix to the one that has the hinge here. Okay, you're going to have another thing, have the hinge here. Okay, so the first step, no matter you're going to use for the case 1 or the case 2, you're going to do the moment distribution, and then you're going to find the K, and then we have 3K, K sub AB, K sub BC, and sorry, K sub AC. AC is this one, K sub BD, that is another column, and for the beam, K sub CD, this is 4EI divided by 5, this one also 4EI divided by 5, and this one also 4EI divided by 5. All of them are equal, and then the second one we find distribution factor, and for sure this distribution factor AC is here, BD is here, they are all 0. Distribution factor AC equal to distribution factor BD equal to 0. Since it's fixed support, okay, give the reason why you put it to be 0. Now you move to this portion. You go to distribution factor CA. This factor CA will be K sub AC divided by K sub AC, and for this one plus K sub CD, and since they are equal, this one will be 0.5, and then you put this one for 0.5, this one 0, okay, and then you go further to distribution factor CD, that is going to be 1 minus 0.5 here, and it's going to be 0.5 CD, and then you come to distribution factor DC, that is going to be K sub CD divided by K sub CD, and you have this one is going to be plus K sub BD. Anyway, you put it, you're going to get this one to be 0.5. Okay, this one is going to be 0.5, and then the next one is going to be this one, distribution factor DB, and this will be 1 minus 0.5 is going to be 0.5, and then this is 0. Now you got to go to the third. You find fixed end moment for case 1. Okay, that is for this case. You have what? You have the column, and this column is going to be AC. You fix both sides, and then it's subjected to 3 kilonewton per meter. You got the fixed end moment here gonna be CA, and it's going to be WL square over 12, and it's going to be 3 times L of 5 square over 12. So you get this one to be 6.25. This is going to be 6.25 kilonewton meter. But what you get this is what? You get this is what? Is the clockwise direction. So the fixed end moment for the CA, this is CA, is going to be positive 6.25, and due to the symmetry of this, you know this one going to be 6.25 kilonewton meter, but it's counterclockwise, so this one going to be minus 6.25. The author member has no fixed end moment, so don't worry. Now we move into what we have. This one gonna be in equilibrium required plus 6.25 times 0 is 0. You may put 0 over here, and then over here what we have is what is going to be required minus of what? Minus 6.25. This is going to be half 3.125 minus 3.125, and then you're going to do what? To do the carry over moment. The moment that occur here, CA, is going to carry over to here, okay, and the moment here, CD, going to carry over here. So what we have, the carry over gonna be something like this, and the value cupcake gonna reduce by a half. That is going to be 1.562, and this is going to be minus 1.562. Now what happened is this one also going to be in equilibrium. This is 0, this is times 0, this is 0. This one will require positive 1.562 to make it in balance, so it's going to times 0.5. That is 0.781. 0.781. Now again there is the moment that's gonna cross. See, it's gonna cross this one, the boundary here. The DC gonna carry over back to this. The DB gonna carry over to here. So you have this one reduced by a half. Let's say this is gonna be positive half of this 0.390. 0.390. Now you have this one again. It must be in balance minus 0.390 times 0. This is 0. And you can see the way the moment distribute across this frame. Okay, this is a good example to show you guys about this. This minus 0.350 is going to be positive. No, it's positive. It's positive 0.390. So this one going to be negative. Okay, half of it 195. 0.195. And now again it's gonna copy the way it's carried over here, and it's going to be reduced by a half. This is going to be minus. This is going to be minus divided by 2 is going to be 0.097. 0.097. You see, when you put more round of it, the number that you can see is going to reduce smaller and smaller until you reach your required number, significant figure that you like to have. Okay, and let me the one that tell you how many rounds you supposed to stop doing so, because of what? Because I should have the same result for all of you guys. If not, I'm going to do very hard job, okay, to grade your work. So this one will do the same thing until you reach this one. Let's say this is going to be half of 0.024, and this one 0.024, and the last one I should stop over here. That is going to be negative. That is going to be 0.012 minus 0.012. Okay, and then you're going to get the answer for the first case over here. And this one, let me put all copy it in the blue, minus 7.91. And then over here, what's the requirement of this? The moment of this one and moment of this one must be equal. Okay, and this one you will get very simple, 0.414. Okay, and based on you, most of the time, if I believe in my calculation, I will calculate only one. For example, I got this one for 2.918. I'm sure this one will be minus 2.918. But if you really careful, you just sum, okay, and check across each other whether it's going to be equal or not. The magnitudes must be equal, but the sign must be different. This one will be minus 8 to 9. So this is positive 0.8 to 9. So this is going to be our first, okay, perform the moment distribution for case 1. And the fifth, okay, you find or compute for the R. Again, due to this, there's supposed to be the horizontal force occur at this end of the column. And per se, let me put over here to make things to compute for the reaction, and say this is going to be column A, C. This is going to be column B, D, and this is for the first column, and this is going to be for the second column. You must carefully put the sign into this. This is going to be negative. Okay, 7.91. This is negative 7.91, and then another one. This is going to be positive 2.918. 2.918, and see, that is the force perform act over here. You must include in the computation, and basis upon this, let's say the force A sub x should be in this direction, and if you summation of the moment at C equal to 0, this is going to be positive. Our A sub x clockwise is going to time by 5, and then what is 2.918 plus 2.918 in the same rotation, but the 7.91 is in the opposite. 7.91 in the opposite, and you also has this one is going to be 3 times 5 plus 3 times 5 and times half of this 2.5. By a careful computation, you will get A sub x to be 8.49. 8.4984 kilonewton. And now you move to this one, and you can see the direction of this one, 0.8 to 9 clockwise, and this one 0.414. And if this one have the clockwise direction, the horizontal force must be in the resistance. Let's say it's going to be B sub x. Summation of the moment about D is 0, and say this is positive. So the B sub x will times 5, and it's going to be equal to 0.829 plus 0.414. So you get the B sub x to be very small, 0.6215, and now you come to what you has for this frame. You must draw the free body diagram. Ajahn, you didn't draw a complete free body diagram. Yes, I didn't do that, because if we draw everything, it's going to be very messed up. That's why we left something for our understanding. And then this one going to be the force of R, and what we have the A sub x here. This is going to be 8.498, okay, 4 kilonewton, and this one in the opposite direction. This is 0.6215, and then you do the summation of x sub x equal to 0, and then you're going to determine the R. So put this one in positive. R plus 8.4984. Okay, it's going to be 0.6215, and this one going to be 3 times 5, and you compute this, you're going to get the R equal to 7.123. Okay, let's say this is going to be 7.123 kilonewton. Okay, now you're going to go by the 6. You're going to assume the fixed end moment for the frame, and then you can see since the column 2 of this has the same EI, okay, and also it has the same length, okay, and the stiffness of this is going to be the same. By doing this, the fixed end moment that occur on the column, all of them must be equal, okay. By understanding, you may say the fixed end moment over here, AC, equal to fixed end moment CA, equal to fixed end moment BD, equal to fixed end moment DB, and I will give you like this. This is what? This is counterclockwise, right? This counterclockwise. I said it's going to be minus 100 kilonewton meter. I will, in the examination, provide you with this assumption. Okay, so it's going to be ACCD. So it's going to occur on the column. That is going to be minus 100, minus 100, minus 100, and minus 100. And I will let you guys to do this computation, and then you will get this one for minus 80.0, and then is minus 60.0, positive 60.0, and then positive 60.0, minus 60.0, and the last one minus 80.0. Now, by doing this number 7, you perform what? Perform the moment distribution, for case 2, and then you get the end moment. Next, you go to the number 8. You're gonna find the R palm. Find R palm. You do the same thing. You have this column A and C, and you have this column B and D, and now you take the moment of this into this portion. You take the moment of this into this portion, and all of them negative 80. That is going to be negative 80. That is going to be 80, and negative 60. That is 60 negative. Okay, and since all of them rotate like this, I'm very sure the force that's occur, that is negative, right? Yeah, it's negative. It's going to be the force A sub x over here. It's going to be, if you summation moment at C equal to 0, you will get the A sub x times 5 equal to 60 plus 80. So your A sub x going to be 140 divided by 5 is going to be 28. Okay, and then come into this one, you get 80, the same thing. You get 80 over here, you get 60 here, and for sure this is going to be your B sub x, and it's going to be 28 kilonewton. And if you draw your frame, okay, if you draw your frame, this is going to be 28 kilonewton. This is also going to be 28 kilonewton. What is going to be your R? This is correct. Yep. Let me check a little bit. Negative. You're going to get the negative here. The negative here occur. Oh, this is wrong. Why? Because it's rotated counterclockwise. This one must rotate in the opposite direction. This one must be in opposite direction. So this one in this direction, this one in this direction. In order you can determine the R palm over here. Okay, it's going to be in this direction, R palm. So summation of x sub x equal to 0. R palm will be 56 kilonewton. Okay, now you find number 9. Okay, you find C. Your C is going to be R divided by R palm. So you get this one 0.12T divided by 56, and then the correction factor you get 0.1272, 0.1272. Now you adjust this, okay? You times this one by this one, and then you will get this one. Let's put it in black. Minus 10.176 minus 7.632 plus 7.632 and plus 7.632 minus 7.632 and then minus 10.176. Now for the summation of this, you get the result. This one for minus 18.086, this one minus 4.714, this one positive 1.714, and they must be equal. This one plus 6.803 minus 6.803. This one must be equal minus 9.762. Now you must put everything, okay, together. Let me move this one a little bit, and then what you're going to have is going to put 18.086 counterclockwise, this one counterclockwise, okay, this one clockwise, this one clockwise, this one counterclockwise, this one counterclockwise, and then you determine the end shear, and then you draw the shear diagram and moment diagram, and you put all of them over here, okay, and finally based upon this you may draw the elastic curve to be something like this one, okay, and then you also can use your correction factor to determine. That is going to be number 10. Number 11, you can find delta, okay, you can find delta. How can you find delta? When you assume this fixed end moment, okay, this fixed end moment to be minus 100, okay, that's fixed end moment 100 is going to be 6 EI delta time over 5 square. So your delta time is going to be 2,500 divided by 6, and to compute it correctly, the delta is going to be the correction factor C, okay, time delta time, and then you will get 0.1272 and time to 2,500 divided by 6. This is going to be your delta, okay. Hey, how about the EI? I lost the EI. Yes, you lost the EI. Adjust it. This one must have the EI here, okay, and then you must put the EI delta over here, and you must put this one EI delta time, and then this one also will have the value of this, okay. You just put this one over to be this one, so it's going to be C time this one, and then you get this one to be a number. Just put it into your calculator. Okay, I will have another 20 minutes for another problem. Let's you guys go back and work on the rest of this problem by yourself. Let me move to this one again. It's not that hard. Only the column are different. Again, this one we will has two frame. One, just put this one, okay, and another one that has this different length of column. Okay, you may just draft it by what? By using the principle of superposition. Don't forget, I don't have much time, so I will leave some writing out. Superposition. Okay, you may say use superposition to separate the frame into two cases. Okay, as shown here. And again, this is fixed. I believe the deflection supposed to be something like this, and then the angle here must hold to be in the normal angle, and this one will come and join like this. The frame has the sidesway delta. You must show this by do the computation. Okay, even though I didn't ask you guys, this one going to be the analysis of the problem is going to be similar to what we did before. Okay, the degree of freedom equal to the degree of indeterminacy, and then what we have, the structure again subjected to this force. We're going to prevent it from the sidesway. That means you got to put the force R over here, and then by doing this you can use the moment distribution method to analyze this case one, and then you let the structure to has the sidesway deformation. By the sidesway deformation, the beam must be stiff. Okay, and now the problem here, you are going to produce the fixed end moment, and the fixed end moment for this column, fixed end moment BD and DB will be different from the fixed end moment occur over here, since the column has the different length. Okay, that is the main point. This problem different from the previous problem and similar to the first one in the PowerPoint. Now, by doing this, your force is this. So summation of F sub X at this one at C equal to 0. So 0 equal to R, and then you get the opposite one. This one you got to move this one in the delta direction. In the delta, you got to move this one in the delta direction. So it's going to be minus R prime, and then you require the correction factor. The correction factor is going to be R, and then divided by R prime. The analysis is going to be the same. They are always the same like this. Okay, and then what we going to do is looking for the K. This problem is going to be more easier than the previous one, because all of these have the same EI. This one has EI. This one has EI. This one has EI. And based on our analysis, this one going to be 4EI over L. This one going to be 4EI over L. And this one also 4EI over L. So the first one, we will find K. And then our first K going to be K sub AC. That is going to be 4EI over 7. Okay, if you put it into your calculator, it's going to be 0.5714. And then you go for the K sub CD. That is going to be 4EI over 7. That is going to be 4.5714. And
the last one is this one, K sub BD. That is going to be 4 EI divided by 5. That is going to be 0.8 EI. Okay, this is going to be the stiffest one. And then the second, you're going to find distribution factor. And again, you just said the distribution factor for AC equal to distribution factor for BD equal to 0. Just put it equal to 0 since it's going to be fixed support. Just put it like this, okay? And then the distribution factor for the author, you must put this one over here, okay? Distribution factor for the CA is going to be K sub AC divided by K sub AC plus this one, K sub CD. Since they are equal, this is going to be 0.5. And then you move to DF on this one, DFCD. That is going to be 1 minus 0.5. You get this one for 0.5. So just put this one 0.5 and put this one 0.5. Now you move into this one, distribution factor DC is going to be K sub what CD divided by K sub CD, and then it's going to plus K sub BD, and then that is going to be 0.5714, and then divided by you may put EI if you like, but you may take it out if you take just EI divided by EI like this. You can do so, and then plus 0.8, and DF DC going to be 0.4167. This one 0.4167. And the last one, you determine DFDB. Just 1 minus 0.4167. That is going to be very simple, 0.5833. Okay, just put this one, 0.5833. And then you are ready to find the fixed end moment for the second case. Just go a little bit further, go to the step number 3, find fixed end moment for case 1. What we have is this frame, very simple. You can determine the fixed end moment cockpit very easy. This is going to be C, this is going to be D, and then this is going to be fixed end moment CD equal to P 4T P. This is 3 meter, 4 meter A, okay, A, and then B square over L square. That is going to be 39.18 kilonewton meter. This is what counterclockwise, so on the CD minus 39.18, and then you have this one also, and this one is going to be fixed end moment DC. DC is going to be 40, opposite to this, going to time 4 times 3 square divided by 7 square. That is going to be 29.39 kilonewton meter, and this is clockwise, so just put positive 29.39. Now you are ready to do the moment distribution. Okay, just move into this. What we have, this one, okay, in balance. Oops. Sorry, I put it wrong. This is 0, 0.5, 0.5, 4167.5833, and then 0, and this one is 39.18. Okay, this one going to be plus 29.39, and this is 0, 0, 0, and then this require positive. Okay, positive. This require positive. Just put it into half of this. Half of this is going to be 19.59. This require positive 19.59. Okay, and then this one 29.39 is positive, so it's require negative here, and then this time here, this is supposed to be 12.25. This one going to be 17.14, and it is in equilibrium, and then it's going to have the carryover moment. The moment here, carry over here. The moment here, carry over here, and it's going to reduce by a half. That is going to be minus 8.57. This is going to be positive 9.80. And then between these two, okay, and 19.59, that is positive. This is negative, okay, and then this is negative 6.13. This is 9.80. Okay, and then you do the same thing. This is going to be in balance by itself since it has zero distribution factor. So this one gonna be positive, this one gonna be negative, and positive 3.07. Okay, 3.07. This one in equilibrium, and this one minus 4.08. This one minus 5.72. Okay, and then it's in equilibrium, and then you do the same thing as before. You got to this one. Okay, carry over moment. Do the same computation until you finish it. You're going to get this summation to be plus 11.93. This one minus 12.02, and this one 23.89 minus 23.89. I should note this one not equal. It's come from the average. Okay, this one 24.10 minus 24.10. They are not equal. I do the average. I did the average for this, and now you go to number 4. You perform moment distribution for case 1, and then number 5 you find R over here, and then basis upon this the computation you will have one for the long column. Please use the ruler to dog it, okay, to make it looking good. Looking good. And then again, this one 11.93 is positive. It's 11.93. This one also positive. This one 23.89. See, and this one 24.01. This one 24.10. Okay, and then this one negative also. This one 12.02. And then if you take the moment over here, if you take the moment, this is rotated like this. You can see this can be the B sub X, and also this one in this direction, this one in this one will be A sub X. And if you do the computation, this one will be 5.12 kilonewton. This one will be 7.22 kilonewton. I assign you guys to work by yourself, and then what we have the case 1 that's show on top over here. Just take it, and then is will has this 5.12 kilonewton, and this one in the opposite direction, sorry, this one 7.22 kilonewton, and then you can do the summation to find the force R. This is going to be the R, and you find the summation of x sub x at what? At this point C, okay, equal to 0. So your R move in this direction is positive. It's going to be plus 5.12 and then equal to 7.22. Okay, or you minus and then equal to 0 if you like. So your R is going to be 2.10 kilonewton, okay, in this direction. Now you finish the first step, and then you got to go to this step by assume the fixed end moment. Let me assume the fixed end moment for the AC to be 50 kilonewton meter, and then this is going to be 50 kilonewton meter. The fixed end moment for the short column must be larger due to the stiffer. Okay, so go further to the next step. Okay, this is going to be number 6. We assume fixed end moment dB equal to fixed end moment BD and equal to 50 kilonewton meter. And if you go back to this one, this is going to be positive. Okay, this all going to be positive. Just put this one in the positive. What we have is this fixed end moment of 50 going to be EI delta palm divided by the length over here of 7 square. Okay, it's going to be 7 square, and then 6 EI delta palm, and then you may have EI delta palm of this to be 408.33. Now the fixed end moment for these two, fixed end moment dB equal to fixed end moment BD equal to 6 EI, and delta palm, the delta over here palm, delta over here palm, they are equal, and then divided by the length 5 square. Now you put this one for 408.3, so you're going to get this one for 98.0 kilonewton meter is going to be positive. So by doing this, this one will be 98, this one will be 98, this one will be 50 and 50. Okay, positive. And then you do the same one as before. Okay, and you will get this one for plus 42.22 plus 34.37 minus 34.37. You must check. Okay, always check, and then this one minus 45.37 plus 45.37 and plus 71.77, and then you check this one. And further, number 7, you perform moment distribution for for case 2. Okay, and you go further. Number 8, you find palm. Again, you have the long column and the short column, and you do the same computation. You take this to be on this column, and you take this two green into this one, and you may compute the reaction, the horizontal force. So just put this one is what is clockwise is 34.37. This one is going to be 42.22. Therefore, we have this one for the A sub x. If you take the moment summation of the moment at C equal to 0, your A sub x is going to be 10.94 kilonewton. And this one is also positive 45.37. And then over here is 71.77. And you do the same thing. Summation of the moment at C equal to 0. You will have what? This one B sub x equal to 45.37 plus 71.77 divided by 5. And then you get this one for 23.43 kilonewton. This one will come from take moment here. A sub x times 7 is going to be 34.37 plus 42.22, and then you get this. Now you do the same thing as above. Okay, as above. Just determine the R palm. Just determine the R palm. You put the force into the column. Okay, this one will be 10.94 kilonewton, and this one will be 23.43 kilonewton, and then you require to determine the R palm here. So you have this one for the R palm. You do the summation of x sub x equal to 0 at C, and then your R palm is going to be the sum of this 34.37 kilonewton, and then and then number 9, you find C. C is equal to, by doing this, R 2.11 divided by 34.37. That is going to be very small number, 0.06109998. Okay, or 0.0611. Okay, you may use this, and then you adjust this one. For example, this one going to be positive 2.58, and this one going to be positive 4.39, and then this one and this one you get minus. Okay, minus 7.63. This one and this one you get positive 14.51, something like this, and then you get all the result. And I would like to show you guys over here. You got the result as shown here. Okay, and also you can draw the shear diagram and the moment diagram as shown here, and please combine them together, okay, to get the shear diagram and moment diagram and draw the elastic curve. And then you can use this correction factor time this assume assume deflection. You get the real deflection, and finally, when you draw the elastic curve, you will get your elastic curve like this. And this is the sidesway, 24.95 divided by EI. So time is out, and sorry for the late lecture for 5 minutes. Anyway, I post the solution of this problem into the Facebook already. I like you go back and work on this and check your result with my result. Thank you very much for your attention, and hope you guys successful for the next examination. Next week we don't have examination, so you are free to prepare for your examination. Have a good day. Bye bye, guys. Thank you very much.